Imagine Sam and Roho are playing chess match in their school. If Sam wins the match, his house Emerald will be leading. In case Roho win the match, his house Sapphire will be the one who will be leading. Both are good players, so we cannot predict that who will be winning the match. Finally, both cannot be a winner. Either Roho or Sam can be a winner. Now the final announcement has come that Sapphire house is leading. From this statement, we can judge that Roho won the match and Sam has lost the match. Similarly, according to the usage of special words, quantifiers, and conditions, there are some rules to validate the statements. Now, let us start with the statements having a special word and. That P and Q is true, the following steps are followed. That is, step 1, show that the statement P is true, and step 2 is to show that the statement Q is also true. Then rule 2 is, if we are dealing with mathematical statement consisting of special word or, then in order to show that the statement P or Q is true, consider the following cases. That is, if the statement P is false, then the statement Q must be true. If the statement Q is false, then the statement P must be true. The next rule, that is, if we are working with the mathematical condition statement if then in order to show that the statement if P then Q is true, one must remember that we can show directly that the statement P is true, then the statement Q is also true. Or as in contrast, we can show the statement Q is false, then the statement P is also false. Then the next rule is, if we are dealing with if and only if statements, then in order to show that the statement P if and only if Q, we need to show the statement P is true, then the statement Q is true, and the statement Q is true, then the statement P is also true. Now let us exemplify these rules. Check whether the following statements is true or not. If x, y element of z such that x and y are odd, then xy is odd. We can notice that the given statement is in the form if P then Q. Yes? Let us write these two as two different statements. The statement P is xy belongs to z such that x and y are odd. What is z? Odd integers. So these are odd. Then the statement Q is saying xy is odd. To validate the statement, let us follow the case 1 of rule 3. That is, to show directly that if the statement P is true, then the statement Q is also true. If we consider first statement x and y are odd integers, then we must prove that the product of x and y is true. As we know, z represents the integers. Odd integers x and y is represented as 2m plus 1, and the second one y is equal to 2n plus 1 for some integers m and n, because odd numbers are represented in this way. Then we know that xy is equal to 2m plus 1 into 2n plus 1. By multiplying, we get 4mn plus 2m plus 2n. This can be reduced by taking 2 as common, which is equal to 2 into 2 mn plus m plus n plus 1. This shows that xy is odd. Therefore, the given statement is what? True. So, why this is odd? Because you see that it is 2 into some number plus 1. So, whenever we are having 2 into some number plus 1, it is always an odd number. Now, if we follow the case 2 of this one, that is in the contrapositive method, we should assume x and y are not odd, then the product xy is also not odd, means what? It is even. The product x and y are even means then x and y must be even. Let us prove this contrapositive statement. Take P, that is x, y element of z such that x and y are odd numbers, which is false, and Q, that is xy is odd, which is also another false statement. Even integers x and y are represented as what? 2m and 2n, not 2m plus 1 and 2n plus 1. That is for odd. This is for even. Then for some integers m and n, then you can see that xy is equal to 2m into 2n, which is equal to 4mn, and this shows that the product xy is what now? Even. Thus, we have shown that not Q implies not P. For this, we clearly understood that to prove P implies Q, it is enough to show that not Q implies not P, which is nothing but the contrapositive of the statement P implies Q. Next, we are going to discuss about validating statements by contradiction. We know contradictions. What does it mean? It means the opposite. To check whether the statement P is true, we should assume that P is not true. That it is not P is true. So either P is not true or not P is true. Then we arrive at some result which says that not Q implies not P, which contradicts our assumption. Therefore, we conclude that P is true. Let us exemplify this. To prove the statement is true, we should assume that the statement is what? A false statement. So here I am taking P, which is root 7, which is an irrational number. We know that rational numbers can be written in the form what? P by Q. So root 7 can be written as A by B, and assuming that A and B have no common factors or they are coprimes, then the square of the equation we get, that is 7 is equal to A square by B square, or you get A square is equal to 7B square, or from that you can write B is equal to A by 7. Here 7 divides A, means 7 is a factor of A. Since 7 is a factor of A, then we can write A is equal to 7C. So we introduce a new integer C so that A can be written as what? 7C. Now squaring both sides, we get A square is equal to 49C square, and comparing A square is equal to 7B square and A square is equal to 49C square, we get 7B square is equal to 49C square, or we get finally C square is equal to B square by 7, or C is equal to B by 7, which shows that 7 divides B also, right? But we have already shown that 7 divides A. This implies that 7 is a common factor of both A and B, which contradicts our earlier assumption, right? It is contradicting the earlier assumption that A and B does not have any common factors. This shows that our assumption, that is root 7 is rational, is what? A wrong statement. Hence the statement root 7 is irrational, and that becomes now a true statement. Next, we can also validate the statement using counter examples. As the name suggests, this is an example to counter the given statement. This method involves giving an example of situation where the statement is not valid. Let us see through an example. By giving a counter example, show that the following statement is false. If n is an odd integer, then n is prime. First of all, we can notice that the given statement is in the form if P then Q. Yes? To prove the statement as false, we need to show that if P then not Q. Let us separate the statements into two different statements. That is, first one P, that is n is an odd integer, Q, n is prime. To prove this, let us take a counter example as n is equal to 9. Here 9 is an odd integer, but not a prime number. Thus we conclude that the given statement is false. We should also remember that in mathematics, counter examples are used to disprove the statements. So whenever you have a statement and you need to disprove it, you can use this as counter examples. And so far we have discussed about how to validate the different statements using different methods. Now you can prove that each radius of a circle is the chord of the circle by a counter example. Can you do that by yourself? Try to do that, and now let's have a quick recap of what all we have learned in this session.
Manorama Horizon, learning made simple.